that has really just helped me. That's why I didn't put many slides on the basics. Anyway, so I take that advantage of it, and that's why, since he has this oversuited time, because actually, just he has used it to explain the basics what I am going to present. So many of you might have visited my lab during this scope meeting, students conference meeting, what we organize annually, and this is also 8th edition, which will be during 4th to 6th of October. So in case you are interested, please feel free to submit articles, and that submission site is still open. And otherwise also, if you want to visit, this is the lab, and then we are open for you to invite. Then once you are
Goutam,
present,
you speak closer to the mic. Sometimes your voice is not coming.
Oh,
clear.
is it?
Okay,
So
yeah,
is it
please.
fine? Because I'm just almost.
It's fine. It's fine. Yeah.
So once you are presenting something, then there is somebody who is really contributing to this one, and I'm happy to have a bunch of very energetic people in my group, and a fantastic class of collaborators, those who help in different aspects. So the students basically, since they handle with photons, and they are also good at playing football. So that is what you see them in the ground, and sometimes they come to lab with a sober dress and perform some of the experiments that I am just going to present. So if I have to just put the expertise what we have been doing or for last 13 years in PRL, I can just put these blobs in that. Let's say my our groups work that can be divided into this kind of planetary system, where we deal with Gaussian laser beam that can go from milliwatt to watt, tens of watts, nanojoule to millijoule, continuous wave femtosecond, all those things are there. We manipulate the spatial structure of the beam, transforming it from Gaussian to different structure beam. Some of them are vortex, hollow Gaussian, ARE, and so on. And we characterize the beam because once you just model the spatial structure of the beam, you get new features, and those features we study. And again, we use those two type of Gaussian or vortex beam, and then do nonlinear interaction. We can generate new wavelengths, polarization, entanglement. Means let's say you can just go to the classical domain and quantum domain for the generation of any wavelength you want, any structure beam, then the entanglement, the quantum communication, that also we have been working. And we have recently started working towards this nonlinear interaction of single photon. So because this nonlinear interaction is very feeble process, and then that's why one need to have high power laser, but we are trying to go for, let's say, use of single photons, and let's see its nonlinear interaction, because if you can just do that one, that can give you a concept of switch. It's a quantum switch. Those are the target, and hopefully you will get some results in the near future. So to explain some of the notable work what we have been doing, we have done in past from quantum and optics and photonics groups in PRL. We have demonstrated this free space quantum communication in PRL itself over a distance of 200 meters. And then we are also involved in basic science, just studying the single photon interference, whether photon interfere with itself. Those kind of studies we have done. We are also involved in developing prototype of this entangled photon source that can be given to others, those who can use these sources for their experiments in quantum optics. We have improved the structure of the entangled photon source to make it more robust, so that it can be used in space condition. And we are also involved in making payloads that from India, we are planning to send some payload to do quantum experiments in space. And we are also demonstrated free space quantum communication in collaboration with ISRO, SAC, and demonstrated video conferencing over a 300 meter as a proof of concept. So these are the things, but unfortunately, I'll not be talking all this. I'll be just talking a completely a different topic, that is quantum sensing. So what the heart of this quantum sensing, what I am going to present is the process which is called parametric unconversion process, where you have a nonlinear crystal and a pump photon goes through the nonlinear crystal. It generates a pair of photons, daughter photons of lower energy, and that is one of them is called signal, another one called idler. And this process maintains two conditions, two important conditions. One is energy conservation, because this is a parametric process. That's why low energy levels are involved in this one. So the generated photons energy will be equal to the pump energy. And they have to also have a momentum matching condition, because since these generated photons have different wavelengths, they will have different refractive index due to the natural normal dispersion of the medium. That's why if you want to really just have that energy transfer from the pump to the generated photons to get substantial output, in that case, you have to maintain a momentum conservation. That is typically called phase matching. And in case of parametric down conversion, this phase matching can be, or any nonlinear process, phase matching can be achieved when typically three techniques are there. One is type 1 phase matching, where the input photon polarization is orthogonal to the generated photons polarization states, but both of them will be of the same polarization states, let's say E or O. In case of type 2, they have orthogonal polarization, the generated photons, but in case of type 0, all the photons and the pump, signal, idler are having the same polarization states. Now, if you see the type 0, in that case, you can see that generated photons are having the same polarization states. That means it's if this process is happening in a collinear geometry, and both of them are having it's in degeneration, where both of them are having the same wavelength. And due to this nonlinear interaction or phase matching condition, their polarization states are equal. Then it's very difficult. It's not possible to extract them from one to the other. That means, just to put in that context, it's a signal cannot be extracted from the idler. Whereas in case of type 2, since they are having orthogonal polarization states, one can use a beam splitter and extract the generated photons, signal idler separately, and then use that for further experiment. Same problem like the type 1 we have in case of type 0, where the photons are co-polarized, collinear, and same wavelength. That's why it's impossible to do this. But then people have just gone for that that's a non-collinear geometry, where the photons are generated in a cone structure, and then the signal and idler will be placed in the diametrically opposite points. Anywhere you can take the diametrically opposite points will be the position of the signal idler. So one can detect the photon from here or here, and then get the pair automatically. In case of type 2, since the polarization degree of freedom is there to extract, so one can use a beam splitter, polarizing beam splitter to extract the photons, or one can use this kind of non-collinear geometry where Joy was showing also, so that generated photons can have this kind of special structure, and the interaction point can give you the sense of superposition and the entanglement. In case of type 0, also recently we realized that one can go from collinear to non-collinear geometry to extract the photon. Okay, so once you have that, what Joy was explaining, so this is the intersection point, give you the entanglement. And once you have this photons generated, one of the way of detecting the photons or understanding whether that they are pair photons. So we typically measure the coincidence. So let's say the photons are pair generated, and then we just analyze and then see the coincidence at the time of arrival of the photons to the two different detectors. And from there we establish whether they are pair photons or not. And then for entanglement study, one can use different parameter estimation like Bell's parameter, state tomography, and spin number. Those are the things what Joy has also explained. So this is basically just for to give you a brief idea about the thing what we are talking about. Okay, and again, this entanglement can be measured from this coincidence. If you are just rotating the polarization state of one of the photon with respect to other, then that gives that interference pattern, and then the visibility of the interference pattern gives the sense of entanglement and so on. Now, when we are talking about this parametric process, as I said previously, it's a safe fuel process. Means it's generate rate is very low. And for any application you want, the power of photons to be high, so that the first thing can be done. Basically, if your photon number is very small and then you have to integrate for a longer period of time, then it's very challenging to establish something. Or for communication also, where you have to do the free space communication for long distance, where the losses are there in the mid channel, then you have to have a large or bright source at the beginning, so that you can entertain the additional losses what you can encounter during the transmission process. So that means that you have to basically just increase the brightness of the source by anyway. Now we analyze what is the possibility. Let's say a parametric non-conversion process is low, and typically you can increase that by using a long interaction length, because the nonlinear interaction depends upon the length of the nonlinear crystal. So it can give you the long higher generation rate. But when you are just using higher long crystal and then type 2 kind of phase matching, where the photons having orthogonal polarization states, then they acquire special walk-off effect. So that as a result of which, even though you are just increasing the length of the nonlinear crystal, basically the effective length of the nonlinear crystal used for this kind of interaction gets limited by this special walk-off. So people have just gone for this periodically poled crystal, where you can control the D coefficient or the nonlinear coefficient of the material by engineering the crystal and access the highest nonlinearity available for a particular direction. Let's say D33 coefficient is the typical one for periodically poled lithium
So
niobate.
Gautam, in between we lost the connection. Can you repeat this is special walk-off?
Oh, okay. I'm sorry. So, yeah. So then one of the technique of increasing the parametric gain is used to use long nonlinear crystal. So when you are just taking nonlinear crystal, long nonlinear crystal, and parametric process is let's say type 2, where the generated photons have orthogonal polarization state, or the pump is having also orthogonal polarization state to the generated photon, then the special walk-off comes in, because the birefringence effect is there. As a result of which, even though we have used long crystal, basically our interaction length is limited by the special walk-off. So basically the increase of length of the nonlinear crystal doesn't really help anyway. So in that case, people have just opted for the periodically poled crystal, where the crystal can be engineered in such a way that you can access the highest nonlinear coefficient of the nonlinear crystal, like D33 coefficient of periodically poled lithium niobate family crystal or tantalate crystal. So again, if you are using type 2 phase matching in that case, then again that comes in picture. The special walk-off also comes in. Even though increase this D coefficient, but the length of the crystal again decided by the special walk-off. So that is why one has to really just go to one should go for some type 0 phase matching, where you have all the advantages of periodically poled nonlinear crystal that can be extracted or utilized in type 0 phase matching, because the walk-off will not be there, and then you have the engineered crystal. But the photon pairs, as I said previously, cannot be since it's a degenerate, wavelength is same, polarization is same, so you cannot really separate that. So for that, we have just come up with a non-collinear type 0 phase matching in 2016 or 17. That time we just came up with that one, where the highest figure of merit of nonlinear crystal we are using, but again we have the flexibility of separating the generated photons through this non-collinear geometry. That's why one can basically access the highest brightness. Means one cannot really just increase brightness of the source by any means except using this type 0 non-collinear phase matching geometry in case of periodically poled crystal. So that is what we use. And then normally, just a periodically poled crystal type 0 phase matching, that is gives a collinear geometry. As you can see, it's a Gaussian spot where where non-converted photons lies at the same position, so it's not possible. But when you reduce the phase matching temperature, we realize that when this collinear geometry is transforming into non-collinear geometry, giving a special distribution in the form of annular ring. So the photons will be distributed over this annular ring, where the unconverted photon will be, the pair photon will be always positioned diametrically opposite points of this ring. So, and then this ring size can be tuned or controlled depending by adjusting the temperature of the crystal. And basically that the phase matching condition is satisfied like this. So the angle is increasing between that two, and then due to the refractive index variation with the nonlinear crystal, and then if you keep on increasing the temperature going towards the collinear geometry, in that case we see all the photons are there. Now if you measure the intensity, as I was saying, it can give you the highest brightness, because when you are measuring the spectral component of the generated photon through this spectrometer, we see that when at the degeneracy we have the highest gain as compared to non-degenerate photons. People have used non-degenerate photon in type 0 phase matching, but in that case we say that on this you are not addressing or accessing the potential of the crystal. So whereas if you are just going for the degeneration, which is challenging due to this the problems I explained, that's why people couldn't really do. But this effect was very readily understood that one can go address this region, the collinear region, and then go to the non-collinear geometry where addressing the degenerate photons. So now if you have this kind of, if you take the snapshot of that using a EMCCD camera, then we'll see that the photons are exactly placed in an angular ring distribution, and any 2 point will show the pair photon. So if the signal is here, idler will be here, and the vice versa, and it will basically always maintain that condition. Now, if you have this, unfortunately, nothing comes free, so it comes with a problem. Problem is, let's say this ring size, what I explained here, this ring size is a temperature-dependent process. So if your temperature is varying, then temperature of the nonlinear crystal is varying, then the ring size will also vary. Like, just to give an example, at 21 degrees centigrade temperature, where we have this ring size, and then it is gradually reducing and going to the collinear geometry. And in that case, if we have a detection system like placed here, which we cannot really change, so it's a fix. In that case, we can see at a particular temperature, the detection system will detect the photon optimally. In other cases, other temperature, it cannot. So if you just measure the let's say coincidence counts while changing the temperature, you can see this kind of variation. And from this, we can analyze, let's say, just to have the coincidence count variation by 10%, we have to stabilize the crystal temperature by 0.12 degrees centigrade. That's very challenging, and especially when you can address it in case of lab condition. When we are going, but for the outdoor experiments, as we are talking in terms of, let's say, quantum communication or sensing, where this kind of, beside that, well, if you can just get that, devise the mechanism also to change the temperature or stabilize the temperature, problem comes. It's not only the temperature. Let's say if the wavelength of the laser, diode laser, which is occasionally, it's frequently happens that diode laser's frequency, it stays at a particular frequency and then it's jump, more jumps are there. It's a very common kind of thing in case of laser diodes. In that case, so if we keep the temperature fixed and then change the wavelength of the laser, we see that this ring is basically changing, as if we will have again the instability and the pair photon detection or coincidence counts. So then we came up with some solution to this one, where we found that we have just projected this ring, which is varying, into a fixed ring. So this ring, even though there is a variation, so you can see here, I have just plotted, even though the temperature of the crystal or the wavelength is changing, the ring size remains unchanged all the time. And that is why when you just have the detection system fixed, it will not really show any variation to this one. And that was basically a substantial change in case of stabilization. So basically, just tolerance of the source to the external perturbation is increased. That is what we say that the more robust system for the entangled photon source. Now, if you have this photon, so I come to the topic now. What we started with. the entangled photon or the pair photon is generated diametrically opposite points, and if we take these two photons and shine on the beam splitter from two ports of the input ports of the beam splitter, then you can have these four situations. One photon can go reflected, another transmitted. Both of them can transmit, both of them can reflect, and one will transmit, other only reflect. So the negative sign comes because the backside reflection is having a pi phase due to the Stokes. So in that case, we can write down the probability of this. Basically, when these photons falling on the beam splitter, they are identical in all degree of freedom. Then in that case, these two terms will cancel each other because they have just opposite phase, and we cannot differentiate whether it's transmitting or reflecting. So in that situation, we will have the first condition where the photons are going into one direction, or the last condition where the photon is going to the other. So if we have now detector, let's say this detector and this detector, we will not see any coincidence between these two detectors. So that is what basically we say that HOM or Hong Ou Mandel interference, photon or two photon interference. And then if we plot the coincidence between these two detectors by changing the delay or distinguishability between the photons. So we are adding distinguishability to the photons. So in that case, the coincidence count will vary. And when they are indistinguishable, then in that case, coincidence count is very low. And when it is again further adjusting, so you'll see. So it will have a curve. This is called HOM curve. And the width of this is very, very interesting parameter to deal with. Another important thing is, let's say, if you have now you see this along any one of these, let's say rising edge or trailing edge, this edge is up. So any fluctuation here in this point, let's say delay variation, very small delay variation, if we can just introduce at this point, we will see the variation, large variation in the coincidence count, depending upon the width. So if we can just modulate the width of this HOM curve, then do sensitive measurement in terms of optical delay. And if we can measure the optical delay, we can measure any physical process that can produce the optical delay to the photons. That is what the basic idea of this quantum sensing using HOM interferometry, what we are talking about. So to address that, we have just devised an experimental setup where we take a photon is a pump laser, diode laser, and do the special filtering, send the laser to the nonlinear crystal, and it's generating, it's a type 0 phase matching PPKT crystal, which is generating pair photon, and that pair photons are divided into two parts, and one of the photon is going in this path. It goes through the beam splitter, and while coming back, it will get reflected and come here. And the other photon is exactly it's going in another path whose length is exactly the same as this length, the other arm length, and they fall on the beam splitter. So now the beam splitter is basically two input ports of the beam splitter is signed with the photons being generated, or pair photons being generated by the nonlinear crystal through the two detectors and seeing their coincidence. And to vary the delay between the photons, what we are using here, we are using this length. This mirror is placed on a translation stage and a feature stage, so where you can just do the fine tuning of the delay and or the cosine. Another important thing I should say, because this reflector M2 is having the normal incidence of the photon on it. That's why any change in this one will not modulate the alignment of the or it will not change the alignment of the system. That's why it's alignment free, even though we are just delaying the thing. So now we take this source. This is the experimental scheme, and then first characterize that. So as I said previously, so this HOM-dip, it depends upon the spectral width, because or the coherence length of the photons. So let's say the photons is a wave packet kind of thing, in this packet form coming. So their coherence length comes in picture. So if the coherence length of the photon spectral width HOM-dip is very large, and if the spectral width spectral width of the photon is very large, then we will have a narrow HOM curve. So if you have a narrow one, then it's more sensitive. If there is a wide one, wide HOM curve, then your sensitivity is low, but the range is high. So we are just addressing those things here. So just to see whether we can control. That means from this we realize that the HOM-dip modulated by simply changing the spectral width of generated photon. So in case of SPDC photon, the intensity distribution can be written in this way. This is the phase mismatch term, and the phase mismatch term can be expanded in that way. This is a pump phase momentum or signal and idler momentum, and then that is coming into the periodic crystal. Now, if we expand this momentum mismatch term, it will be in the Taylor series expansion. This first term is basically the phase matching condition, what we are adjusting by putting the grating period. So it's automatically 0. Second term is a group velocity mismatch. So the group velocity between the interactive photon and will give the value of spectral width. And third one is the group velocity dispersion of the photon. So that is basically just coming in the form of this term. Now, when you are in case of phase matching condition, when you are adjusting the grating period and crystal temperature, we are making the first term 0. In that case, second term takes the lead to find out the spectral bandwidth of the unconverted photons. So basically, it's come in the form of 1 by L. But when you are talking about degenerate photons, so the group velocity between the photons is small or 0. In that case, the third term, which is weakly dependent upon the wavelength or length of the crystal, weakly dependent on the length of the crystal, decide the spectral bandwidth of the unconverted photon. That is what we understand from nonlinear optics. So in that case, the spectral bandwidth of the unconverted photon can be presented in the inverse of square root of L. That means if we can just reduce the length of the crystal, the spectral bandwidth of the nonlinear generated photons can be modulated or increased. And again, the spectral bandwidth, the coherence length, we just try to find the relation. The HOM-dip width is proportional to the root of length of the crystal. So that means if we crystal length, then we can reduce the HOM-dip width. That means we can go to the more sensitive measurements. If we use a longer crystal, then the sensitivity of the HOM curve or the sensing will be low. That is what we are just playing. So to do that one, we have done the experiment. We have used nonlinear crystal of various lengths, periodical poled crystal of various lengths, 1 millimeter, 2 millimeter to 30 millimeters is a 5 lengths we have used. And then we have measured the coincidence count or HOM-dip. You can see the HOM-dip is exactly everybody is having almost the same position of the HOM-dip. And the visibility of both the curves, all the curves is basically ranging from 86 to 90% in that range. It's not varying too much. Still, it's more than 50% to establish that it's a quantum effect. And then you can see when you are reducing the length of the crystal, the HOM-dip is reducing. That is what we wanted to see. Say for 1 millimeter crystal, we get a spectral, it's a HOM-dip width is very narrow. Now the question, obviously question comes that we should further reduce this one and then go for higher spectral bandwidth or lower HOM-dip width. But again, if you reduce the length of the crystal, you are reducing the number of photons being generated. So there is a trade-off. We have to stop somewhere. And beside that, so alternatively, people can use a small thin crystal and then use ultrafast laser. That is what typically people use to modulate the spectral bandwidth of the unconverted photon. But in that case, use of say ultrafast laser itself is a bulky process. So we are talking about this in-field demonstration of the kind of system. So in that case, you can really just entertain such kind of bulky system. So that is why we are just trying to see that on whether using a continuous wave, basically in all these measurements what we are talking about, it's just a continuous wave diode laser. That means entire experimental setup or architecture comes into the small package, and it is a maintenance is low. So that is what we are addressing. And then instead of changing the spectral bandwidth of the pump itself, we are basically changing the crystal length and increasing the sensitivity of the HOM curve. So while these HOM curves are there, so we have basically measured the spectral bandwidth of the unconverted photon and the full width half maximum of the HOM curve. So you can see when the crystal length is increasing, HOM-dip with is HOM-dip and dip width is increasing. That's the red dots as expected, because when the crystal length is increasing, the spectral bandwidth is reducing, so HOM-dip width will go up. Whereas the spectral bandwidth, when you are reducing the crystal length from 32 to 1 millimeter, so you see that when the spectral bandwidth is almost 163 nanometer. It's a huge spectral bandwidth of the nonlinear crystal. So, and just to experimentally, since the crystal length is small, in this case, we can really measure using spectrometer, but first two data points we have compared. Experimentally, we have measured it with the spectral bandwidth. So in this case, they are exactly matching the 30 nanometer and 37 nanometer kind of thing for 20. But for other lower crystal lengths, we couldn't measure because the CCD camera used for measuring the spectral bandwidth of the down-converted photon is having a higher threshold, so we couldn't really reach the number of photons required for such kind of measurement. But in case somebody designed a spectrometer using single photon detector, then we can perhaps measure the spectral bandwidth. Since it's matching for the 2 points, we expect that it will be matching for the other point, and the solid line is basically the theoretical fit. So from this slides, what I wanted to emphasize that we can control the length of the crystal, which will control the spectral bandwidth of the down-converted photon, and in turn it will change the HOM-dip width, and that is what we are trying to do. So again, if you see this one, so we have just zoomed that curve what I presented previously. So for all the crystal lengths, as you can see, if I am just taking my reference point here, so for 1 millimeter crystal, the slope of the curve is very large as compared to the 30 millimeter crystal. So we are reducing the length of the crystal, but we are gaining in terms of sensitivity. But as expected, the range of the system is reducing from here. That is a 20 micron delay it can support, or 50 micron delay, 16 micron delay it can support. In this case, it can maximum range comes into around 5 micrometer. So you can go for higher sensitivity to the lower range, but in the other case, you can go to the lower sensitivity but higher range. So basically, you have to just choose the crystal length. From this study, we can choose the crystal length depending upon the need. So if you are looking for a large range measurement, so you have to just go for longer crystal. If you are looking for high sensitive measurement, in that case, we have to just use smaller crystal length. Okay, so using this one, then what we did, we basically just measure that. So what I was just showing all this coincidence counts is basically just recorded over 20 millisecond integration time. Normally people use 1 second or so, but we have just used it for 20 millisecond, but still we just see substantial coincidence counts that is used, because that can be useful. Still, it can be useful for any practical application. And why you have to use 20 milliseconds? Because you want to measure it for faster processes. So if my integration time is long, then I cannot really do fast measurement, or any process which is changing the delay dynamically, you cannot really measure. That's why we are just trying to address this one by reducing this the integration time. So in that case, you have to basically have a bright source. So if your source is not bright enough, in lower integration time, the coincidence count will be too small. It's close to the noise level. So that is what we wanted to avoid. That is very reason. So once we have this, then what we did, we just use the piezo, and then use applied voltage, which we have calibrated the piezoelectric piezo by using this exactly same technique. I'll explain that on. But believe me that when we are just adjusting the position of the stage by this nanometer, this is not the picture. This is a translation stage which has certain resolution in the nanometer. So we have to change this position. Then we can see about just 60 nanometer shift. We have a variation in the coincidence. That also we have just recorded it to see whether we are basically seeing this coincidence are merging or not. And we can see well separated this coincidence counts even recorded for 600 seconds. So there is not match. So you can, since you can identify this coincidence value variation, so we can easily comfortably say that we can, using this HOM interferometer, we can measure a static delay by 60 nanometer or even less than that. So that is what is the static displacement. So then we wanted to go for the dynamic sensing. Like let's say we want to measure something vibrating. Let's say small low frequency vibrations or low amplitude vibration or at lower frequency, like for an example, earthquake having some amplitudes coming in that range. So can we just measure that? To measure before going for that one, so what we did, we calibrated our piezo system, because it was not a closed loop one. So we calibrated it, we changed the applied voltage and then measure the displacement by using the translation stage. Basically, we have just moved the translation stage by a particular distance x, and we recorded the initial coincidence count and the final coincidence count, then increase the applied voltage to the piezo to bring that initial coincidence count back. So when it is coming back, we see that when the piezo has displaced by the same distance what your translation stage has moved in opposite direction. So that is how we have just done. And then you can go up to 70 volt, we can go, and then the piezo can be displaced by 35 micron. And it was exactly, according to the specifications given by the vendor. Once we have this calibration of the piezo, now we have used a rectangular signal to the piezo, because we know that one, and then we know the voltage. So we change the voltage, and then we recorded the coincidence count. Initially, we have just by linear stage, we have adjusted the initial delay of between the photons to go to one of the points at the center of this HOM curve, and there we have just applied a voltage, a small voltage, and as you can see from here, we expect that amplification. That is what is amplified getting here. And in that case, we measure that for set delay, we measure the optical delay using this one. So just from the peak to peak variation of this coincidence count and previous calibration data, we can just find out how much is the variation or amplitude of the driving voltage. So that is what we can just adjust it different voltage or a different amplitude, and then record it up to 3.5 micron you can do, because the range of this HOM curve using 1 millimeter nonlinear crystal is 4 micron or 3 micron in that range. So that's why you have just restricted in this one. And then we have repeated this experiment twice, and then every time we are seeing that red and black, you see that they are superinputs. So we can record any distance around in this range, as I said previously, for the static displacement, that can also occur in this range. So again, what we have done, we have also measured the frequency of the driving signal. So the driving signal we change from 1 hertz to below 1 hertz, it can easily measure. So anything beyond 1 hertz, we have increased the driving frequency, and then measured the frequency from the coincidence count variation data, and then we see the one-to-one correspondence between the set frequency and the measured frequency. And how we have measured the frequency? Basically, we have taken this one and did the Fourier transform. And then when we are doing the Fourier transform, we see that exact frequency. And for 1 to like this up to 10, we can go. But you can see when you are increasing the frequency, that the peak size is reducing. That is because of the fact that the integration for this kind of system or integration where you used is basically 50. That means for each for the number of data points it's required, basically counts something 50 by f. F is the driving frequency. So just to replicate the shape, we need substantial number of data points. So when you are increasing the frequency, then the number of points to replicate this wavefront or applied signal is reducing. That is why this peak amplitude is reducing, and then we are seeing also second harmonic of this driving frequency. But safely we can say we can just go up to 8 hertz using this technique. That means 8 hertz is near to the video range, video frame rate kind of thing. So we are basically using a HOM interferometer, and we are measuring dynamical signal, which is having the frequency variation near the video range. That is something, just nobody has done. And basically, just there is certain report, but not using this technique, but some other technique. And in that case, by Paul QIQT, but that is basically using very low frequency signal. We are talking about high frequency signal. Okay, then once this is calibrated, we have the complete idea about the system. We try to put some arbitrary signal and then try to measure it. And in that case, we see this exactly the signal is replicating, and it's confirming that it can be used. Then we have studied further to see whether we can achieve high precision. This one, there is some mathematics about this camera bound in this case. So using this camera bound, we have to use our experimental condition, that Fisher information curve, because you can see this camera bound is let's say if it is equal, then 1 by a number of iteration into Fisher information, or if I did that the value, the product is inverse. So now if I can somehow increase this Fisher information, then I can go for a lower number of iteration to reach to the bound, or we can get the higher precision at lower time. That is what we are just targeting. So the Fisher information, how we can increase, that also can be increased by changing the width of the HM curve. So that is what we have modified this Fisher information by plugging in our experimental parameters in the form of crystal layer. So that is what we use, and then plotted the Fisher information with the optical delay for different crystal length. As you can see, when the crystal length is 1 millimeter, then the Fisher information is enhanced substantially. Something is 35 into the -4 per micron square, basically 17 times enhancement in the Fisher information. That means the number of data points required or iteration required, we can easily reduce, divide it by 17 times. So that is what we studied. And then for different crystal length, we have just accordingly studied the peak value of the Fisher information. And it's as expected, it's dropping when we are using longer crystal. That means high sensitive measurement to address vision, or we need basically thin nonlinear crystal. Then we have used this maximum likelihood measurement, use this iteration. So basically what we have selected 2 points, x1 and x2, and then we have moved the piezo from between x1 and x2, and then recorded the coincidence counts. From there you can see the separation between these 2 points remains unchanged. So if you zoom it, is like this, and then the delay, if you just measure, then initially that is a variance is very high because the points are there, large number of points is required to reduce the variance. But as small as in a 3000 data points integration time or experiment times or iteration, if we go, then exactly we can just go for the 5 micron kind of precision, because in this measurement actually we adjusted the separation between these two to be 5 micron, 5 nanometer. So we can reach even 5,000 or 4,000 iterations. So 4,000 iterations, 6 hertz will require only 19 minutes. Previously, people used to integrate it for hours and hours doing this experiment, if you see that previous paper. But in this case, we are showing that we are just going to that lower iteration time. That means it's giving you the possibility of doing high precision measurement in a realizable time scale. So then we have repeated that one for different delay, estimated delay, and then we see that as expected, we see some kind of variation. And as expected, this number of the increase of Fisher information reduces the number of iterations required to reach to the let's say precision, and that goes up. Let's say 14,000 counts, 14,000 iteration or the time accordingly if we are just using lower Fisher information value. So once we have that characterized, we realize, okay, that's great. It means it's working. Next one. Then we try to say, let's say, can we just measure any physical parameter that influences delay, so that we can measure, means effectively you can utilize it for the sensing. So for that, what we did, we just put keeping this experimental setup fixed, we put a sample here in one of the arms. Okay, the sample can be anything. So in our experiment, we have basically used a different nonlinear crystal or a different medium. So then what will happen without crystal? This was the HOM curve, and due to the insertion of this any optical component, it will increase that optical path, so we have to reduce this. So we get that the shift or jump of this HOM curve to this point. So from this time delay, we can find out what is the refractive index of the medium. Okay, that is what we have just used different nonlinear crystals, and then we see that on how the refractive index is varying for different crystal lengths, and the theoretical value is also there in this. But unfortunately, so you can just take that value, that's perfectly all right. There is a substantial jump in the refractive index, one can measure. But if you see this one, this jump, when we are going for the very precise measurement of the refractive index, in that case, that reliable consideration of the peak position or dip position in both the cases is erroneous. So it can give you additional error. So one cannot really just use the shift of this HOM-dip to find out very precise variation in the refractive index. In that case, what we did, we use exactly that measurement in that HOM curve. So we placed our HOM, initial position of the HOM curve here, and then we change the refractive index of nonlinear crystal with temperature, because all these periodically poled crystals has a refractive index dependent, temperature dependent refractive index. So that is what we have just put there using it's a small narrow HOM-dip for 4 micron, and this one is for long crystal length. So it's a 16 micron HOM-dip. So as expected, we see that the range of this refractive index variation is larger in this case, but the resolution is low, because you can see that slope is low. But in this case, the refractive index slope, you can see that is coming in, the resolution is coming into 10 to the minus 6 order. That's a lot. So we can just measure the temperature variation of the refractive index of an nonlinear crystal with a resolution of 10 to the minus 6. So using simply by using that HOM interferometer. With this, I think I have just come and then to the conclusion. What I talked about, it's mentioned here. We have demonstrated the control of spectral conduit of the pair photon, and it is controlling the length of the crystal. We can just change the width of the HOM-dip and its Fisher information, and demonstrated that static and optical or dynamic sensing of optical delay in attosecond time scales. We have also demonstrated that arbitrary amplitude and frequency, any optical signal that is in having arbitrary amplitude and frequency, definitely in the range we can measure, and use of the Fisher information can give us ultimate precision, and increase of this one gives us the possibility of going towards almost the real-time kind of high precision measurement. So because the time is something around 19, but we can further increase that using other alternative. So using this HOM interferometry, we also saw how one can precisely measure the variation of the refractive index of medium as a function of temperature, and any system that can give the path between the photons, that physical process can also be measured using this technique that we are exploring. And typically people have used this kind of HOM interferometry for, let's say, quantum microscopy and many other applications or imaging. So that is what we are just targeting in the future. With this, I would like to thank you all for your time, and I'm open for questions. So I hope I have maintained the time. Thank you very much.
Okay, thank you, Goutam. So you can unmute and ask question from Goutam. Hello. There are questions. Please go ahead and ask questions. We have next talk as well. Hello.
Can I ask?
Yeah. Sure.
Thank you for your talk. What type of improvements you have obtained by using Rao-Kramer bound?
Yeah, so exactly. So Kramer-Rao bound is there. That bound is there. It's inversely proportional to 1 by n into f. Okay, f is the Fisher information, and n is the number of iterations you are just going. So if you keep on increasing the iteration, then you can just reach the bound, and then you can means the bound can be saturated. Okay. So now the question is, let's say product of two terms that is what we are just dealing with. So either you can just increase the number of iteration n, or increase the Fisher information. So here we are basically targeting to increase the Fisher information, and that Fisher information, since it's depends on the width of the HOM curve. So we show that one by playing with that HOM-dip through the spectral bandwidth of the nonlinear photon generated photons, we can modify the Fisher information, and that is basically 17 times enhancement in the Fisher information than the previous reports. So that is why we are just getting very low number of iteration or lower time. Now, if you can just reach to this ultimate precision in real time, that is what people are just targeting. So we are just going one step towards that. Reduce that 119 to 19. Previously, it's a few hours. Now it's 19 minutes. It has come into the minutes. So we are just trying to, let's say, we can just go to even shorter time range, so that ultimate precision can be used for the Fisher information measurement or quantum sensing or measurements, that kind of thing.
Okay, thank you. Question: What is your interpretation of brightness? Paired photon source, it is I can understand.
So brightness is basically, in case of this one, let's say per second, if we are integrating how many number of photons are coming.
Thank you.
That is what, and then per unit spectral width and many other parameters. But for in a simple version, I can say that so brightness is basically the number of photons we are detecting per second.
Thank you.
If it is very high, then we can get a substantial detection. Otherwise, we are detecting, let's say, 10 coincidence per second, and that is basically just going into that let's say dark count and background close to that. So we cannot really just do much with that. So that's why one has to really increase the brightness of the source, so that the signal itself, signal to noise ratio is very high.
Any other question? Okay, if there are no more questions, if there are any questions, somebody was asking. Hello, please go ahead. I don't see any question in chat box. Somebody was asking and stopped. Really. Anyway, if there are no more questions, let's thank Goutam once again. Thank you, Goutam.
Thank you very much. Thank you.
For giving your time and giving such a nice talk.
Thank you.